Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A Level Chemistry Unit 2 for January 2021. This is the Part 3 video. I'll put the link to the Part 1 as well as the Part 2 video below the discussion box. Let's begin with the first question here. Question 21 says, this question is about ethanoic acid and some related salts. A test to confirm the presence of an aqueous acid is adding a small amount of solid sodium carbonate to the solution. Remember, this is a solid. So they say describe two observations you would see in this test. We know this aqueous acid, when you add sodium carbonate, carbon dioxide gas is going to be produced because a carbonate reacting with an acid produces carbon dioxide. So effervescence is going to be observed. Effervescence of a colorless gas occurs. That is an observation. The other observation is the solid is going to disappear as the solid reacts with the acid. So a white solid, sodium carbonate, will disappear or it will dissolve. So let's continue to the next part. Here they say sodium ethanoate is a component of reusable hand warmers. In use, a supersaturated solution of sodium ethanoate recrystallizes to form solid hydrated sodium ethanoate, releasing energy. So here they've given us the reaction for between sodium ethanoate and water producing this product here. It's a hydrated salt. And the enthalpy change for that reaction is negative 19.7 kilojoules per mole. Then they say a hand warmer has a mass of 63.2 grams and forms 20.1 gram of hydrated sodium ethanoate on crystallization. They want you to calculate the maximum temperature reached by the hand warmer if its initial temperature is 5 degrees Celsius. They have given us the specific capacity of the hand warmer at 3 joule per degree Celsius per gram. I began by calculating the molar mass of the hydrated salt, which is 136 gram per mole. And then using this, I went on to find the number of moles of that hydrated salt, which is going to be mass divided by the molar mass. The mass we're given is 20.1, and the molar mass we have calculated is that, giving us this as the number of moles. Now we know this is an exothermic reaction, and for an exothermic reaction, delta H is equal to negative Q over N. Because this is exothermic, I know it's negative 19.7, so I can drop the negative, and that negative will be dropped. So we can say delta H is Q over N. So making Q the subject is going to be N times delta H. Substituting the values here, I have that as the number of moles, and delta H was given, but it's in kilojoules, so I have to multiply times 1,000 to convert it to joule per mole. So the final answer I got is in joules, 2911.5 joules, and that is going to be the Q. Now we also feed that information into this equation. Q is mc delta T. Remember, we want to find the value for delta T. So making delta T the subject is going to be equal to Q over mc. Again, remember this Q has to be in joules. So that here, divide by the mass we are given is 63.2 grams, and the specific capacity is 3. So when I substituted, I got this as the value. That is for delta T. However, delta T should be the final temperature minus the initial temperature because, again, this is an exothermic reaction. So T final should be the initial temperature plus delta T. So since delta T is that, which I got here, and the initial temperature was 5, the final temperature is going to be 20.3562. I rounded out to 3 significant figures, and it came out to be 20.4 degrees Celsius. That is the value we're looking for. Moving on. So here they say ammonium ethanoate, which is that, is used to control the pH of foods. It can be formed by the reaction of pure ethanoic acid with ammonium carbonate. Calculate the standard enthalpy change for this reaction by completing the Hess cycle and using the data shown. So I'm going to go down here to show you the data in the table. Here we are given enthalpy changes of formation of the different compounds we have here. So, and again, going back here, they say ammonium ethanoate is used. So if we are forming ammonium ethanoate, a reaction is going to be between ethanoic acid and ammonium carbonate because those are the values we're given here. So we have ethanoic acid, ammonium carbonate producing this, and then we have carbon dioxide and water for that whole reaction. However, they've given us the enthalpies of formation. So remember, an enthalpy change of formation is when 1 mole of a certain compound is formed from its element at standard condition. So to form this, we need to have carbon, we need to have hydrogen, and we need to have oxygen. To form this one here, we need carbon, we need hydrogen, we need nitrogen, and we need oxygen. So you can see I have nitrogen, hydrogen, oxygen, and carbon as elements in this table. So then I have to see how many carbons are this side. We have 1, 2 times 2, that is 4, plus 1 here, there are 5. That's why I have a 5. I'm talking about the total, 5 carbons. And then nitrogens, let's see, these are 2. So we have only N2 here. And then for, let me see, for hydrogens, we have 4 times 2, 8, and then plus 8. So that is going to be 16, meaning it should be 8 H2 to create 6 hydrogen atoms. And lastly, for oxygen, I need to see these are 2, so that's 4, plus 3, that is 7. To create 7 using an element, it should be 7 over 2 or 2. So I have balanced everything here, giving me that. Then for the other side, we can see it should be the same, because if that gives us that, that should give us that. Now, fitting into the enthalpy changes of formation, because this here is to form that, but remember here we're forming 2 moles of that. This is per mole, but for 2 moles, I need to multiply this times 2. So you can see 2 times that. And then for formation of this one here, which is ammonium carbonate, we see it's negative 939.9. Since we are forming 1 mole, it's going to be exactly that. So the total enthalpy for this is 2 times the enthalpy for 1 of that, plus the enthalpy for formation of that, which is going to give me a total of this. That plus that gives me that for that part. And then for this other side, we can see enthalpy of formation of 1 mole of ammonium ethanoate is that, but we are forming 2, so that times 2, that is what you see here. Formation of 1 mole of carbon dioxide is that, so I added it here, and formation of 1 mole of water is going to be that, which I added here, combining everything. For that side, I got that. Now to find this, I should reverse this and then use that as it is. So it should be positive 1908.9 minus 1851.9. That should give me the enthalpy change, which you can see here, and it's going to be positive 57 kilojoule per mole. That is my final answer. So you do that, you get 5 marks. Moving on. Here they say ammonium carbonate, which is that, is an ingredient in cleaning solutions for camera lenses. These are aqueous solutions which contain no more than 1.8 gram of ammonium carbonate in 100 centimeters cubed of solution. So here we can see a mass concentration, 1.8 grams in that. Because they say no more, I think we can see here no more, it means that should be the maximum. It should be 1.8 in 100 centimeters cubed solution. So here they say calculate the maximum concentration in mole per decimeter cubed of ammonium carbonate in such a solution. To have a maximum concentration, 1.8 grams should be dissolved in that. So I say 1.8 grams of that in 100 centimeters cubed of the solution. So in this case, 100 centimeters cubed, I converted this into decimeters by dividing by 1,000. So it means I get 0.1 decimeters cubed. I wanted to get my mass concentration. So concentration should be that divided by that, which is 1.8 divided by 0.1, giving me 18 grams per decimeter cubed. But the question wanted us to find concentration in mole per decimeter cubed. So to do that, I need to divide by the molar mass, which is going to be 18 divided by 96, which gives me 0.1875 mole per decimeter cubed. To write it to 3 significant figures is 0.188 mole per decimeter cubed, and that is my answer. So this brings us to the end of question 21. Let us continue to question 22. Question 22 says potassium chlorate 5, which is that, is a crystalline solid used in fireworks. It is produced by the Liebig process in 2 stages. So stage 1, chlorine gas is passed through hot calcium hydroxide solution, forming calcium chlorate, which is that. And then so we can see this reaction for that. And then in stage 2, potassium chloride solution is then added to form potassium chlorate 5. The reaction goes on like that. Then they say the solution is heated and then allowed to crystallize. The crystals are filtered off, and the remaining filtrate is evaporated further to obtain more crystals. They want you to write an overall equation for the Liebig process. State symbols are not required. So if this reaction leads to that reaction, I cancelled out things that were on opposite sides that were similar. So here we can see this appears on the other side and it appears here. We can cancel it out. And then anything else that doesn't appear on either side, we can just combine. So we get that, which is that, plus that, which is that, and that, which is that, on the left side. On the right side, we have that. However, it's the same as this, so we can combine the two to produce 6 calcium chloride, plus we have this one here, it's 2 that, and then plus 6 water, which is that. So this is going to be okay. Or you could write divide by 2 because they're all multiples of 2. So divide by 2, we get 3. Divide by 2, we get 3. Divide by 2, it's 1. Divide by 2, 3. Divide by 2, 1. And divide by 2, 3. So if you wrote this equation or that equation, it is acceptable. Moving on. Here they say calculate the overall atomic economy by mass for the production of potassium chlorate 5 using your equation in A1. Here I began by looking at the molar mass of potassium chlorate, which is, for potassium we can see is 39.1, and for chlorine 35.5, and 3 oxygens is going to be 48. Adding everything up, we get 122.6 gram per mole. Then the molar mass, remember we are calculating atomic economy, so we need to find the molar mass. The molar mass of the products we have, the molar mass of this is that is that is that. This is the major product. This is for all the other products. So we know that atomic economy is going to be the molar mass of the intended product divided by the molar mass of all products times 100. So that here divided by that times 100 gives us 24.0%. That is the overall atomic economy. Moving on. Here they say explain the type of reaction that takes place in stage 1 of the labeling process using oxidation numbers. So if we're using oxidation numbers, we want to know if the reaction is a reduction or if it's oxidation. Now looking at calcium, we see this is calcium 2 plus, still 2 plus. Oxygen is not in O2, it's not in hydrogen peroxide, it's not attached to fluorine, so we can know it's going to be -2. Hydrogen is the same thing, it's going to be 2 plus 1 here as well as there, so there is no change here. Here we can see there is chlorine, which is an element, or you could say chlorine molecule, but on the other side we see it's a chloride. So it means chlorine is being converted from 0 to -1 oxidation state, that is reduction. However, there is another compound containing chlorine, and this is a ClO3, list like that. That is going to be oxidation state +5, so we can see +5. So we can see chlorine is oxidized from 0 to 5 and is reduced from 0 to -1. That is a disproportionation reaction. So here I said it is a disproportionation reaction since chlorine is oxidized from 0 oxidation state in that to +5 oxidation state in that, as well as being reduced to -1 oxidation state in that. So you get 3 marks for that. Down here they say the crystals of potassium chlorate 5 formed also contain some halide ion impurities. They want you to describe a chemical test on a solution of these crystals to confirm that the impurities present are chloride ions rather than bromide and include the expected results. So this is basically testing a halide, and then later we observe if it's a white precipitate or if it's going to be a cream precipitate. So to do that, you have to use silver nitrate and nitric acid. So here I said, to the sample, add dilute nitric acid followed by silver nitrate. A white precipitate will form, but since it is visually hard to distinguish from the precipitate formed by bromide, because here we form, with bromide we form a cream precipitate, and with chloride we form a white precipitate, but these colors are so hard to distinguish. So we have to add dilute ammonia to further confirm. So here I said, since they're visually hard to distinguish from the precipitate formed by bromide, add dilute ammonia. When you do that, the precipitate dissolves to prove that it's chloride. When you add dilute ammonia, the bromide precipitate will not dissolve, and that is how you can tell them apart. Moving on. Here they say 1.52 grams of impure potassium chlorate 5 formed in the Liebig process was heated until the mass of the solid remaining was constant at 1.02 grams. The reaction that occurred is as below. So they say the impurities present did not decompose on heating. Calculate the percentage purity of the sample and give your answer in an appropriate number of significant figures. So the key thing is we have that, which is 1.52. So, and we see, they say the mass remaining was 1.02. So we can see the oxygen that left was that. So that is the mass of oxygen. And then they say the impurities present did not decompose on heating. They want you to calculate the percentage purity of the sample and give your answer to an appropriate number of significant figures. So we say the mass of oxygen is going to be 1.52 minus the 1.02, giving us 0.5, which is the sample left is that, and the sample original sample is that. so that is the mass of oxygen. The next part is to calculate the moles of oxygen, which should be 0.5 divided by the molar mass of oxygen, giving us that. And next, the moles of potassium chlorate, which are that. You can see the ratio is 3 to 2, so it's going to be 2 divided by 3 times the moles of oxygen, giving us that as the number of moles of potassium chlorate. Now we need to find the molar mass of potassium chlorate. We already got it previously. It was 122.6 gram per mole. So we're going to use that as well as the number of moles to find the mass. The mass of potassium chlorate should be moles times molar mass, which is the number of moles calculated here, and the molar mass, which we have here, giving us 1.27709 grams. However, we are looking for the purity. The mass of potassium chlorate in the impure sample is that. However, we know the original sample was 1.52 grams, which means the percentage purity is the mass of potassium chlorate in the impure sample divided by 1.52 times 100, and that is going to give us 84.019, which is about 84%. That is the percentage. And again, to go back to the question, they said calculate the percentage purity of the sample. So purity is going to be the mass of the chlorate divided by the total mass times 100. Moving on. Here they say in fireworks, potassium chlorate 5 decomposes. This thermal decomposition takes place in 2 stages with a solid catalyst. So there is this decomposition to form that, and then further decomposition to form that. They say give the systemic name of this one here. To do that, we need to find the oxidation state of chlorine. We know this is potassium chlorate, but we need to find the oxidation state of chlorine. To do that, I know that of potassium is 1, giving chlorine to be X, and we know in this compound oxygen has -2 oxidation state. Since therefore oxygens, -2 times 4 gives us -8, and we equate the whole thing to 0 because the oxidation state of a compound is 0. So here, making X the subject, I got X is equal to 7. So it means this is potassium chlorate 7. That is my answer here. The next part says a student investigated the role of the catalyst in this reaction. So they see procedure. Step 1, heat a sample potassium chlorate in a test tube with a known mass of insoluble catalyst until the mass remains constant. In step 2, they say mix the contents of the test tube with water. Since we know the catalyst is insoluble, it means it will not dissolve, so it can be easily filtered out as the soluble contents dissolve in the water. So step 3, they say filter the mixture and rinse with deionized water. Step 4, dry the remaining solid. And step 5, measure the mass of the dry solid. This dry solid is the catalyst. So it means if the mass is constant, the catalyst is going to be not used up and it's going to be the same as you put it before. So here they say explain how each of the steps in this procedure is needed to show that the catalyst is not used up in this reaction. So I said for step 1, heating a sample to a constant mass ensures that all the potassium chlorate decomposes. Then step 2, mixing with water ensures that the product, which is potassium chloride, dissolves in the water, meaning anything that has not dissolved is going to be the catalyst. Then step 3, rinsing the product removes potassium chloride, which would remain on the solid and adds to the mass of the catalyst. Step 4, drying ensures that the remaining mass is that of the catalyst, meaning without the water. Step 5, the mass of the solid is recorded at the end of the experiment to make sure that it's the same as the starting mass. If it is not the same, then the catalyst was used up. Let us continue. Here they say explain using the diagram how a catalyst speeds up a chemical reaction. So here we have the number of particles with energy on the vertical axis and energy on the horizontal axis. We know if a reaction is not catalyzed, the activation energy is going to be a little bit higher, but adding a catalyst creates a new pathway with lower activation energy, meaning we have another pathway here with low activation energy. So we're going to have more fraction of molecules are going to have energy equal to or greater than activation energy to have a higher rate of reaction. So here I said, without a catalyst, the fraction of molecules with energy equal to or greater than activation energy is lower. However, when a catalyst is used, a new pathway with lower activation energy is created. So more molecules have energy equal to or greater than activation energy. So there are higher chances of having successful collisions, and the rate of reaction is potentially increased. Be very careful, you have to put successful collisions. you have to talk about a new pathway. A new pathway here with low activation energy, as well as the whatever you have drawn here, this one here, to get the marks that you're looking for. So this brings us to the end of question 22, as well as the end to this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.